Okay, graphing rational functions. There are 7 steps for us to follow to make this work in our favor. So first off, find the horizontal or oblique asymptotes and or in behavior first. Factor and find vertical asymptotes. And sometimes you're going to have discrepancies, which we call a hole. The third step is to find the x-intercepts, letting the numerator equals to 0. Then you're going to find the y-intercepts. Well, that's just letting x equal 0. Step 5 says you're going to take the function and make it equal to the horizontal or oblique asymptote to check for intersections. So that means that if your horizontal asymptote is not 0, if it's not 0, you're going to do number 5. If it is 0, you just skip number 5. Number 6 says make a number list with key points so you can kind of effectively graph your function. Number 7 is to graph it. Make sure that you do these in order because that's kind of like your recipe, and that makes your graph kind of look more reasonable. All right, a couple summary we want to look at. Our summary is that, for one, if the denominator is 2, or let's say 2 or bigger, the denominator is bigger than the numerator for their degrees, you're going to have what we call a horizontal asymptote at 0. That means you do not have to do number 5, step 5 that we talked about, if this is what we call a proper fraction. If the degree on the numerator is 2 more than the denominator, then you're going to have what we call no asymptote. If the degree on the top is 1 more than the degree on the bottom, it's still improper. You're going to have to do long division and find what we call the slant or the oblique asymptote. That's kind of like a line. If your degrees are the same, leading degrees are the same, then what we're going to have is the coefficients of that. So for example, this is 2 and 2, this is 1, this is going to be 3 over 1, which is just y equals 1/3 as your horizontal asymptote. So let's do an example. We have an example on the top, example on the bottom. So if they are the same degree, that means that the coefficient is going to be y equals 2. So we're just looking at the coefficients in front of the x's. They are the same degrees, so they're going to be the coefficient of 2 over 1. That means technically as x approaches some value, let's say it approaches infinity or gets close to, the numerator and the denominator are going to be they're going to be the same. But the numerator is going to be 2 times as bigger as the denominator. So that kind of tells you that these grow, but it's going to be 2 times more than the denominator. So that's why we get what we call a horizontal asymptote at y equals 2. So that's a summary of kind of what we are trying to look at when we try to graph these. So let's look at our progress. So let's look at one here. So graph the rational functions. Let's go ahead and graph this one. We have a rational function, look at the numerator and the denominator. It's all in order. Remember, we always try to find the order first. So order first. That means that it follows x2, x1, x2, x1, 0. So order first, check. Then we're going to say, okay, we're going to follow the steps. So step 1, first put the stuff in order, the leading coefficients, and then simplify. This tells you what your in behavior is about. Now, we can kind of look at this and we can kind of see, okay, well, we can almost tell what the in behavior is. So remember, in behavior is that if you can have 2 positive, you can have 1 positive, 1 negative down here. It can also be flip-flop. You can also have 2 down. So if we want to kind of look at this, and like this. Okay, those are our 4 in behavior that can happen. Now, since this is the degrees are the same. Remember, we kind of talked about as our limit approaches infinity that these two bottoms are going to be the same, so the coefficient's going to be 3/1, which is a horizontal asymptote. All right, after you get step 1 all figured out, let's look at step 2. Factor everything. Factor everything that you can. Now, what we're trying to look for discontinuities. We're looking for holes, something that might happen in the graph. Fortunately, this one does not have any discrepancies. Well, it has a discrepancy at the vertical asymptotes because remember, our denominator cannot be 0. So that happens when -4 and at 3. So you kind of can picture that in your head, or you can picture that if you have something and you have -4, you're going to have what we call a vertical asymptote there, and at 3 you have a vertical asymptote. That means these VAs, the vertical asymptotes, you cannot go through these at all. They're big barriers. So that's what this polynomial has right now. Okay, so nothing cancels out, but -4 and 3 are what we call your vertical asymptotes. These are kind of like your discontinuities, so there's breaks in the graphs. So if they do not cancel out, there's no vertical asymptote. So for example, if you had a hole, let's say that these crossed out. That means that if they cross out, there will be no vertical asymptote at that point. Instead, it'd be a hole. So maybe that -4 would cross out. Let's say -4 would cross out. Well, if that was a hole, there actually would not be a vertical asymptote there. It would be a hole instead. And what you would do to get that hole is that you would put this value back into your function, and that would give you a y. We practice some of those. All right, step 3 says we need to find the x-intercepts. The x-intercepts happen when the numerator is actually equal to 0. So on our top, we have a numerator of this being factored out. That means that 3 equals to 0, so you're going to have 3 equals to 0, you're going to have x equal to 0, and x minus 1 equal to 0. And I want you to be very careful. These all have multiplicity. Remember, multiplicity is saying how many times does your graph cross. If it's a multiplicity of 2, it's going to touch, or what we call bounce off. If it's a multiplicity of, let's say, odd, it's going to go through. So multiplicity tells you kind of, is it a bounce or is it a through? And that happens at an even or an odd. So this one, 3x equals 0. 3x times 0, so I guess 3x equals 0. Instead, that's what we call a cross, multiplicity of 1. So that's a cross. This is also a cross. Then we're going to look at what we call y-intercepts. The y-intercepts tell us, well, something more about the graph. Where does it cross on the y-axis? And you just let x equals 0, you find y equals 0 as well. All right, since number 1 was a horizontal asymptote, it was this. If the horizontal asymptote isn't y equals 0, or the x-axis in this case, I'm hoping that you understand that's the x-axis, then your graph will intersect the horizontal asymptote. So sometimes this is interesting because if you have a horizontal asymptote, your graph might come in contact with the horizontal asymptote. Yeah, it kind of will intersect somewhere and kind of bounce off a little bit and come back towards the horizontal asymptote. So what you're going to do is set your original problem to that horizontal asymptote, which was 3. So you're going to go back to your regular function. You're going to go back to your regular function, and you're going to put in 3. You're going to put in 3. So once you put in 3, you're going to have something like this. So you're going to set the function to what you got as your horizontal asymptote, 3. Then you're going to cross multiply. And if you cross multiply, you're going to get something like this. So you cross multiply. Remember, this is 3 over 1, so that's going to be 3 times all this junk, and then that's going to be 1 times all that. And that's going to happen there. Then you're going to start doing some simplifying. And then what happens is that your x's don't cancel out. So if your x's do not cancel out, you're going to have a hit on the horizontal asymptote at 6. For example, this one. Well, what does that mean? Well, that means at 6, you need to figure out where does it hit on the y or on your horizontal asymptote. You're going to take that number, which is 6, and you're going to put it back into your function, your original function. Remember how this was equal to y or f of x? You're going to put that 6 back into your regular function. And that's kind of what I showed you here. And that's why I got 3. So if your x's, so if all your x's cancel out, then your graph does not cross the horizontal asymptote. But since they do not cross out, 6 at 6, 3 is where it's going to hit the horizontal asymptote. And how I found that, remember, I'm going to put this 6 back into your original function, which was y, and you're going to get something out. You should get 3. So that's kind of step number 5. So you do have a step 5 in here. Number 6 says that I'm going to do a little bit of graphing. And here's what I'm going to do. I'm going to make a little table of x values or x axes, and I'm going to make sure I put my vertical asymptotes in. Then I'm going to pick, and then I'm going to say, do I have any x-intercepts? Then I'm going to start picking some points, some other points to help me out that's not on the vertical asymptotes. So I'm going to pick a -5. If I put -5 back into my original function, my original problem, I get 11.25. If I take -1 for say, because that's not on my function, put -1, I will get a -0.5 out of it. If I put 1.5, I get 1/15 out of my function. And if I take 4, remember, at 3 is your vertical asymptote. If I put a 3, I get 4.5. These additional points tell me some more points on the graph. And that helps me kind of pinpoint what the graph is doing. And so if I take all this junk and I take all this information and put it here, I come out with something like this. And you can see 6, 3. That point right there says that is where this graph comes in contact with my horizontal asymptote, and then it kind of hits there and kind of bounces off. It kind of goes straight. And your vertical asymptotes are kind of like your big barriers. You can't go through those. And the reason we made those extra points over here, some of these kind of points right here they're right here. You have an idea of what's going on with your other graph. And that's why these extra points really come in contact. Remember, if you put an X in, you should get a Y out. That's kind of what this is saying. If I put an X in, I should get a Y. And these 2 points right here, I think are my x-intercepts, which says that if this graph goes up, it might go through one of these. It goes through one of these points, it hits the x-intercepts, and then it kind of goes back down. And that's why I put, and this point up here says that this is right there. That point right there is that one. So that one says, okay, well, that means my graph has to go above the horizontal asymptote. So this is the only one that crosses. So that's kind of like the idea with all this, kind of seeing what your functions are doing, and they are looking weird. I mean, the reason they're looking weird like that because they are it's a division problem. It's a broken graph, and the discontinuities are at the vertical asymptotes, so it doesn't cross. That's why you get like a break of 3 different kinds of graphs. It looks like. All right. Let's look at one with a hole. So we have our 2 fractions, or our fractions. They have the same degree. Well, that's good for us. We don't have to do a whole lot of long division. And that means our horizontal asymptote is going to be 2. The degrees are the same. That tells me my horizontal asymptote. So you have to do number 5, step 5. Step 2 says I'm going to factor the top and the bottom. And this is what happens when I factor this with this one. So this is the factorization of this one. I'm hoping that you're going to see that you have the top and then not in the bottom. See how those are the same and they're fractions. I mean of factors. So let's kind of like think about this. If you had 3x divided by 6x, you can cross out the sixes. If you had x minus 1 divided by x minus 1, oh, those can cross out. So we can cross out what we call factors. We can cross out factors. Well, in this case, x minus 2 says, okay, I get to go away. I cross out. So that means I have a serious issue here. I have what we call a hole at 2. And how do I get 2 is that, remember, you're going to take this x minus 2, which is a factor there, set it equal to 0, and you solve for x. But that at 2 gives me a hole. Now, remember, this is a vertical asymptote at x minus 2. But back in my summary, if I had a hole instead of a vertical asymptote, that takes place. That takes precedent of that. So at this, x equals 2 is not a vertical asymptote. It is a hole instead. So how do you figure out the other part of the hole? Well, we have the x. Why can't we find the y? Well, we're going to plug in 2 to our function. You can plug it back up here if you want and see what you get. And that's our new form. That's our new form. I'm hoping that you get to see that from this. Now, if you plug in 2, your hole is at 3/4. That's your hole. So if you plug this in, you're going to find out that there is actually a hole there. There's nothing there at 2. And you're probably thinking, well, 3/4 is there. It really isn't. That's kind of how we're trying to find a location of that hole. We know that at x equals 2, it is a vertical asymptote, but remember, it's not anymore. All right. So that's kind of what we call the vertical asymptote, but remember, it's not. It's a hole. All right. Next 3, x-intercepts. And remember, when we factored our form, this was our top number only. We don't have the x minus 2 anymore. It's just that 1. So that's our x-intercept. That's our only x-intercept at 1/2. Okay, step 4. Step 4 says find the y-intercept. Well, let x equal 0. We got -1/2. Okay, remember step 5? Well, step 5, we had a horizontal asymptote at 2. So we're going to take that number and we're going to put it back into our factored form. It's okay, you can put it into your factored form, not your original one. It actually would be the same thing, by the way. So if you plug this in and cross multiply, remember this becomes 2/1. This is 2/1. You're going to cross multiply. And what's going to happen is, oh boy, look what happens. No, untrue, not possible. They do not intersect. -1 does not equal 4. So all your x's disappeared. That's kind of what you're looking for because that helps you because that tells you that your horizontal asymptote at 2, your graph does not touch your horizontal asymptote at all. Now keep going to number 6. This is where we're going to put a little bit of information in. So we're going to put our vertical asymptotes. Remember, we have a hole there at y equals 2. So we kind of we do have a vertical asymptote, but really it's not it's a hole now. And we still have a hole here. So what's that tell us? Well, we have one cross, what we call an x-intercept. But if we try to graph this, we really don't have an idea of what our graph's going to look like. So let's pick some extra points above and beyond. So here we go. So -3, we get 7. If we plug in 1, we get 1/3. If we plug in 3, we get 1. Now the more numbers you put on there, the better your graph is going to appear. And after that, you plug all that in, you get this, and you can kind of see the hole right there. That's your hole. So in calculus, we're going to look at what we call limits. And as you are approaching that hole, we don't really get there, but you're kind of approaching that hole going like this, and you don't really get there because there's a hole. So there's a discrepancy. This is not continuous. This is not continuous graph. So that's kind of what's going on when you're trying to do some of these with this. So hopefully that this made a little bit more sense. And try some of these. And let's go back to our summary here. So horizontal, no horizontal asymptote. Sorry, horizontal asymptote is 2. This is going to be no asymptote. This is going to be the long division or oblique. This is going to be the coefficient. And there's kind of what's going on. So that's kind of the end of what we call the graphing rational functions. Well, hopefully this helped. Take care.